All right, everyone, we are finally done with rocks and minerals. I know that was a long chapter, but we are finally done. We are going to move on to motion. This is chapter 6. We are going to start talking about lesson 1, describing motion. It starts on page 214. So chapter 6, lesson 1, 214, describing motion. Grab your highlighters, grab your pencils, and let's get started. All right. When you are done, we are going to be able to describe when is an object actually in motion. All right, so when is an object actually in motion? Some vocab words we're going to learn about are motion, reference point. We're going to learn about the International System of Units, which we've already talked about, and we're going to learn about distance. So let's get started. Start off with the My Planet Diary, a little bit about history. Talk about Nicholas Copernicus. Why would anyone think that Earth moves around the sun? After all, on a clear day, you can see the sun moves across the sky. But Polish astronomer Nicholas Copernicus realized that an object revolving around you from left to right looks the same as an object standing still while you rotate from right to left. On the revolution of the heavenly spheres, he wrote, "Every apparent change in respective position is due to motion of the object observed, or of the observer, or indeed to an equal change of both." This book was published in 1543. It was a summary of more than 30 years of Copernicus's studies on the solar system. So the question you have to write, it says, write your answer to the question below. It says, for thousands of years, many people thought Earth was the center of the universe. Name one possible reason why they thought this. So you guys learned a lot about the solar system last year in 5th grade. And then there's a little bit of information over here about why people would think that the Earth was the center of the solar system. Write your answer in this section below. Pause the video. Do it now. All right, you should have unpaused the video, answered that question. And let's talk about when an object is in motion. Sorry, I'm trying to look at my screen and get this zoomed in. All right, get your highlighters out. Let's get it started. When is an object in motion? Deciding if an object is in motion isn't as easy as you might think. For example, you're probably sitting in a car as you read this book. Are you moving? Parts of you are. Your eyes blink and your chest moves up and down. But you would probably say that you are not moving. An object is in motion if its position changes relative to another object. I want you to highlight that sentence. An object is in motion if its position changes relative to another object. Because your position relative to your chair does not change, you could say that you are not in motion. So, I'm going to move this up, extreme close-up, we don't like those. All right, so because you are sitting in the car, even if you're not in the car right now, you could be just sitting at home, which you're probably just sitting at your desk, or in your bed, I don't know, at your kitchen table. I need to shut the light off. That's way better. Whew. But because you're sitting and you're not moving, but the car is moving, you're not in motion. The car is in motion. Just like if I'm in my chair, the chair is moving, my body's not moving. Okay? My chair moved, I'm not moving. Chair's moving, I'm not moving. Okay? All right, let's get back to it. Reference point. To decide if you are moving, use your chair as a reference point. A reference point is a place or object used for comparison to determine if something is in motion. Highlight that sentence. Oops. A reference point is a place or object used for comparison to determine if something is in motion. An object is in motion if it changes position relative to a reference point. Objects that are fixed relative to Earth, such as a building, a tree, or a sign, make good reference points. You may already know what happens if your reference point is moving relative to Earth. Have you ever been in a school bus parked next to another school bus? Suddenly, you think that your bus is moving backwards. When you look out the window again for a fixed point, you find that your bus isn't moving at all. The other bus is moving forward. Your bus seemed to be moving backwards because you had used another bus as a reference point. Did you know? Ooh, did I scare you? Did you know? Because of Earth's spin, the stars appear to move in circular arcs across the sky. Only the North Star remains in a fixed position. Historically, sailors have used the North Star to help them navigate. Pretty cool. Did you know that? I bet you some of you knew that because you guys are all smart. Most of you probably knew that because you guys are all smart. All right, time to use your pencil now. Told you to grab a highlighter and a pencil. Hope you guys listen to me. Get out your pencils. Figure 1, it says art in motion, reference point. The top photo was taken shortly before the bottom photo. Answer the following questions. Did the car that the boy is in move, or did the car in the background move? Explain your answer. So look at these two photos. So did the car that the boy was in move, or did this car move? Explain. Number 2, what objects in the photo make good reference points? So remember, a reference point is that point of comparison to determine if something's in motion. So it's something that's going to not move to see if something's in motion. So actually, if we go back up here, I want you to highlight objects that are fixed relative to Earth, such as buildings, a tree, or a sign make good reference points. Highlight that, because that'll help you answer number 2 at the bottom of this page. Awesome. So number 1, did the boy's car move or did the car in the background move? Number 2, which objects make good reference points? Pause the video and answer it right now. Boom! You unpause the video. Now you're ready to move on. Relative motion. Let's talk about it. Relative motion. If you use your chair as a reference point as you sit and read, you are not moving. If you choose another object as a reference point, you may be moving. Suppose you use the sun as your reference point instead of your chair. If you compare your position to the sun, you are moving quite rapidly because you and your chair are on Earth, which revolves around the sun. Earth moves around the sun at a speed of about 30 kilometers every second. That's fast, just saying. So you and everything else on Earth are moving that quickly as well. Going that fast could travel from New York to Los Angeles in about 2 minutes. Relative to the sun, both you and the chair are in motion, but because you are moving with the Earth, you do not seem to be moving. Okay, so it all depends on what you choose for your reference point if you're in motion or not. We're going to do the apply it. So, apply it. The people in the photo are riding on a spinning carousel. Are the people moving relative to each other? Are they moving relative to the objects on the ground? Number 2, how is your choice of reference point important when describing the people's motion? The motion of the people. All right, you should have paused the video to answer that. If you didn't, pause it now. All right, let's do measuring distance. I counted down. That was my 5, 4, 3, 2, 1. That was my counting down to the distance. Measuring distance. We've talked about measuring distance before, way back at the beginning of the year, but we're going to talk about it again. So, measuring distance. To describe motion completely, you need to use units of measurement. Scientists use a system of measurement called the International Systems of Unit, or in French, Système International, SI. Distance is the length of the path between 2 points. Highlight the definition for distance. We should all know what distance is. It's the distance between 2 points, the length between 2 points. The SI unit for length is meters. The distance from the floor to a doorknob is about 1 meter. Scientists use other units to measure distance much smaller or much larger than a meter. For example, the width of the spider shown in figure 2 can be measured in centimeters, which is done in cm. The prefix centi means 1/100th. A centimeter is 1/100th of a meter, so there is 100 centimeters in a meter. For length smaller than a centimeter, a millimeter, mm, is used. The prefix milli means 1,000th. So there are 1,000 millimeters in a meter. Distances much longer than a meter can be used as kilometers, km. The prefix kilo means 1,000. So there are 1,000 meters in a kilometer. A straight line between San Francisco and Boston would measure about 4,300 kilometers. Figure 2. Let's do measuring distance. This picture freaks me out. Can't do it. Boom. Gives me the heebie-jeebies. All right. It says the unit of length that you use to measure distance depends on the size of the distance. Review. Fill in the common conversion for length. 1 meter equals how many millimeters? 1 meter equals how many centimeters? 1 kilometer equals how many meters? All of that can be found in the reading. I read all of that to you. What is the distance in centimeters from point A to point B? How many of these spiders would fit side by side in length of 1 meter? So how many spiders could fit in 1 meter? And that's all for motion, guys. That's it for lesson 1 in motion. That's all you got to do. Great times. All right. Make sure you answer these questions. That's only 1, 2, 3, 4, 5, 6, 7. 7 easy questions. You can do it. Couple things to highlight. Not very hard. You got this. All right. 8 if you count the My Planet Diary. So you could do it. Let me know if you have any questions. Please make sure you do this. If I see you in class, you can show me in class. If I do not see you in class, please upload pictures onto Google Classroom. And have a wonderful day.